that we have done with several people, different projects. And Elena Gora, Jorge Antesana, Diana Carvajal, Catherine Hare, and Ursula Monte. This is not only multi-tile, but it's multi-nations also. So, because it's kind of late and everybody's very, very tired, probably, I want to make a very simple and slow talk. So we're concerned with constructing Riesz spaces of exponential. So what do you mean by that? We take a domain, omega in RD, always we work in RD, measurable set, and we say that the sequence of real numbers, when you put it as a frequencies of exponential, it's a Riesz basis of L2 of omega, if it is complete, this set in L2, and is satisfied these inequalities. So everybody knows that. And so we're interested to characterize these domains omega that support a basis of exponential. And unfortunately, there are very few examples of that. For example, we don't know if a triangle in the plane or a circle in the plane support the basis of exponential. This is an open problem. So for orthonormal basis, it's even worse, but you saw that maybe for Riesz basis, it's not so worse, and still it's a very hard problem. So not too many years ago, nobody knows there exists a set that does not support the basis of exponential. And Kozma and Alesky in 2022 found the first example of a bounded set, the real line, that does not admit a Riesz basis exponential. So still there are sets that do not have Riesz basis exponential. So why we want to get Riesz basis exponential? Well, you can do Fourier analysis in an interval, and that's what for periodic function, that's what Fourier did. But you want to do it in more different domains that are disconnected, for example, then you need to have a basis of exponential. Okay? And then you can do all the results. You can maybe translate many results of Fourier analysis in the interval in this case. So that's the main motivation to find this basis. And the other side, if you take a domain omega and take the Paley-Wiener associated to that domain, I mean all the functions in L2 whose Fourier transform has support in this domain, then we have this equivalence. It's a sequence of exponential. It's a Riesz basis of L2 of omega if and only if this sequence of numbers is a set of sampling interpolation of P W omega. So you have a Riesz basis exponential, you can make sampling and interpolation in the Paley-Wiener associated. So that's the second motivation of this problem. So the classical example everybody knows is when you take a function E hat to be a Fourier transform. The Fourier transform of the function is a characteristic function of omega, and then they translate the reproducing kernels of PW omega, and in this case, the translation is on orthonormal basis, see? And the frequencies are the integral. In this case, it's orthonormal basis. Okay, so multitiles. What we are going to do is to look at the particular domains. The general problem is very difficult. So to consider a set omega of finite measure and a complete lattice in RD. And then we say that this set is a K-tile. K is an integer, positive integer, that satisfies this property. So what set satisfies this possible? This equality is there is an easy way to describe this set. Is that a set case tile is a union of case set of representative of the quotient of RD with the lattice. Okay. So we are looking at this set. It's a union of set of representatives. No, you can add a set of measure zero. One important thing is this paragraph here. If you have a K-tile, then you can look at the set lambda that for each omega, and you add lambda, this is positive. It's 1 in that case. And then for each omega, you get lambda 1, lambda k, that belong, when you add W, belong to the set. So the main idea of this is that the set omega is completely characterized one time you know all these vectors. Yes, this vector depend of omega. Is that clear? For example, if this is my tile with a C square lattice, and that's a set of representative. For each point here, you have one element in the lattice that you get a representative here and the equivalent here. Okay, and if you have something this side, you get one here and one here. So, but you have to put some order in the linear order in the lattice because it's not, you get confused. Okay, so what about Riesz spaces and multitiles? Okay, it's lattice is in RD is just a multiplication of invertible matrix with lattice C to the D. So take the dual lattice, and we will call H, and Nirlev and Grespat, and later Konousakis proved the following theorem. If you have a bounded measure of the set, and bounded here is very important, that K tiles by lattice lambda, then there exist K vectors in RD, such that when you translate the lattice by these sets, and then you get a Riesz spaces of L2 of omega. Okay, so this is the first result, and Nirlev and Grespat make a proof with a hypothesis of the set omega is Riemann integral. That means that the boundary have measure zero. Soon, Konousakis make another proof, remove this hypothesis, and prove the same. So let us call this, if you look at the set of frequencies, this is the lattice H, that is the dual of the one that K-tile, translated by K numbers. So if the frequencies are of this type, we will call this basis of exponential, structure basis of exponential, okay? So we're looking now for this kind of basis in K-tile. So Konousakis showed that actually the real numbers, well, the real vectors in RD, A1, AK, can be many of them, because the vectors that do not satisfy this is a meager set in RD to the K, okay? We later proved that actually almost every K numbers, K vectors you choose, this works. So you have many bases of structured bases of exponential, just picking A1, AK randomly. So the question now is converse true. I mean, if you have a set that supports a structure basis exponential, it is true that it's a k-tile. Is the number of translators is just k. And this is true, and even for unbounded omega. So what is next now in this talk is try to see if this theorem is still true when the omega is unbounded. Okay? So Kolusakis asked a question if it's true, this question, if it's true for any unbounded omega. And we found this simple counterexample that this is a two-tile, okay? For the lattice C. You have one set of representative, and the second one is just this thing, the union of these intervals. And this is clearly unbounded. It's not too hard to prove that does not support a structured basis exponential. It may support a basis exponential, but not in a structured one. Okay, so with my student, we try to answer this question try to characterize actually the unbounded sets that satisfy that support the basis of structured exponentials. And for that, we use some result from the Schiff invariant spaces. Okay. So this is a theorem that says that if you have a Paley-Wiener space for some domain omega, and omega cation by lambda, then this set has a Riesz basis. Okay, the translation of Vj is a Riesz basis for Pw of omega is equivalent to that this matrix is bounded above and below. So how this result happen? Well, this is a kind of know that so you know the paper of Marcin Bownik in Schiff invariant space. It says that if you have a Schiff invariant space that translate by assumes the integer is a Riesz basis. You have a generator that gives a Riesz basis. Then the Fourier transform of this Riesz basis, the generator of this Riesz basis, when you look at the orbits, have to be a Riesz basis for each omega, as you call it, the fibers of the functions, and with the same constant, uniform constant, okay? So in that case, when these orbits are infinite in the general case, but in our case, we only have, sorry, the orbits are this one. In our case, we only need to just add k element of the lattice, that are the one that when you translate the characteristic function is not zero. And then this has to be now a Riesz basis with a uniform constant for each omega. So okay, we have these results. So we want to find then our set of generators now are the Fourier transform inverse of the exponential multiplied by the characteristic function of omega. Okay, so how this matrix change when you specialize for this particular case? So if you replace the function phi1, pn for kernels of the Paley-Wiener space, you get this matrix. So now the problem is the following. For which lambdas and real vectors A1, AK, this matrix is bounded away from 0 and bounded above. So you take here, look, you have any vectors A1, AK, and lambda 1, lambda k are the ones that are non-zero when you translate by omega. So actually, when you make the replacement here, there is another matrix that appears, not only that one, but the other one is unitary, so you can remove it, okay? Okay, so now we have this problem. We want to find a set omega that is the same that to find and a lattice. It's the same to find lambda 1, lambda k for each omega, that this matrix have this property. So the first idea we have is we have a condition. So let's call O of lambda. O is came from orbits of this set that characterize the set omega. So the lambda 1, lambda 2, etc. is the one that omega plus lambda 1, omega plus lambda 2, and so on are in the set. Then we have a definition. Assume that omega is admissible. We say that it's admissible. See, there exists a vector in the dual lattice and a natural number, so that when you make the dot product between this vector and every one of the, for each fixed w, every one of the lambda, these are all different in the ck, a different modulus k, a modulus n, sorry, that there exists an n at this hub. So if you get a set omega that have this property, then this is admit a structured basis of exponential. And it happened every bounded omega satisfies that. So this new class of sets omega that we call admissible, in particular, include all the ones that already know that have a basis exponent. So the bad news is that there exists a multitile that is not admissible and has a structured basis exponents. So this condition is only sufficient, and it's not a characterization. Okay, so we need something else. And okay, let me explain this before you read the transparency. We have all this set of lambda 1, lambda k for each omega, one for each omega. This is a countable set because lattice is countable. See? And then we have all this subset of the lattice to the k. Okay. This is this set is included in the lattice to the k. This is subset of the lattice to the k, are the one that correspond to the set omega. And then the lattice is a group. It's a locally compact group, actually. But it's discrete, okay. And then the idea here is to take this set that could have, remember that if the set is unbounded, this element could be very large as you want. But then we want to somehow to get to the original case. That in the original case, the set was bounded, so the lambda that you use for the set also bounded. And then, but this is a lattice. It's never bounded. And this set probably is not bounded. The idea is to make a compactification of the set. And this is a little bit technical now. There is some people that are in group theory locally compact group. You know that you have a group, locally compact group. You have the dual, the Pontryagin dual, that are the homomorphisms in the group that go to the disk, to the circle. And then the idea is we take this group, the dual of a lattice. Well, this is done for CD to make it a little bit easier. So the dual of the group CD is the torus, C to the D. So we take K parts, K times this group, and then take the Pontryagin dual. Okay, Pontryagin dual is C to the K. But what happened with the trick with the compactification is to change the topology of this group and take the discrete topology. The dual is going to be bigger, okay? And let's say something a little bit faster. Since the characters of the dual are homomorphisms in a discrete set, are all continuous. But the dual of this group with the original topology are only the continuous one for that topology. So to make it short, we have that we note that this as the dual of T to the D to the K with the Pontryagin with the discrete topology of T to the K. This contains the dual, the normal dual, and since this was a subset of this is a subset of this. But this is inside a compact set because that the Born topology is compact. I make this compact. So if we closure this, we get a compact set. So the idea is to take this lambda 1, lambda k, embedded in the Pontryagin dual with the Born topology and closure. So we have lambda 1, lambda k, and then the extra one that came with a limit, okay, when we close this. I'm sorry, this is a little bit complicated, but now we take, as before, but we take now characters in this group, and take any number, any vectors there, and define this matrix. The only difference is this matrix with the original one, that here we have only the characters corresponding to C to the D, and here we have the new character that in some moment could be one of those. So the idea is now to put the condition on this matrix, not in that one. So it's a little bit stronger because here we have more elements. And then we using what? This include all these matrices. So if we ask that this matrix satisfies this equation, then we are done. But should be necessary for the system of structured basis? Well, we prove that yes. And so the condition is that the determinant of this matrix is different from C. So that is the final result. So unbounded multitile or any multitile have a structured basis of exponential if and only if the determinant of this matrix is different from C. Okay, so recently there is a new result that in place to take this set of lambda 1, lambda k, they set exponential in this case, but now this matrix, they observe that live in the torus to the D, in the torus to a la k times k, because this is the matrix of k element times k element. So this and T is the torus is compact. So they use this a similar result, but now in place to ask that the determinant that we saw before is different from 0. Now we have a determinant of this matrix is bigger than 0. Okay, so I have 3 minutes. I finish here the mathematics. And happy birthday, Chris. You're very young. I want to bring here this picture. This picture is from 1991. And I thought that these were all the students of John at that moment. But John told me that there's 2 left, two that's not here, missing. And this was the year that we knew Chris, 35 years ago, and all these people, and John. And thank you to a little bit, not a little bit, a big part of this is Jim Burns that organized this meeting that was spectacular. I mean, we enjoyed a lot, and for us, Ursula and me, was very, very good because we were new in this area of wavelets, and we all of a sudden we see all these big shots that were in that meeting. So thank you everybody for being here, and thank you, Chris.